I cannot give you the current date and time. However, I can give you extensive details about cotton to yarn manufacturing. Let's dive into the extensive details of each step in the cotton to yarn manufacturing process, complete with examples where applicable. Objective: to separate cotton fibers, or lint, from seeds, leaves, and other trash, and to compact the lint into bales for transport. Now, where does this take place? Well, ginning usually happens at a ginning mill, which might be near the cotton fields rather than the spinning factory itself. The spinning factory receives pre-ginned bales. Let's talk about the process details, starting with harvesting. Manual picking is still practiced in some regions, though it's less common for large-scale production due to labor costs. Pickers go through fields by hand, selecting mature cotton bolls, and this typically yields cleaner cotton. On the other hand, mechanical harvesting is the dominant method for large-scale operations. Spindle pickers use revolving spindles that pull the lint from the open bolls, leaving the plant largely intact. They're efficient but can pick up more plant trash. Meanwhile, stripper harvesters strip the entire cotton boll, including lint, seeds, burrs, and all from the plant. This method is faster and cheaper but results in cotton with higher trash content, requiring more intensive cleaning at the gin. Ginning is where raw cotton, also called seed cotton, arrives at the gin. First, the seed cotton passes through various cleaning machines, like stick machines and green leaf machines, to remove large foreign matter such as sticks, leaves, and dirt. The most common type for upland cotton is the saw gin. Here, circular saws with teeth pull the fibers through narrow ribs, leaving the seeds behind. For long staple cotton, like Pima or Egyptian cotton, which is more delicate, roller gins are used. In this method, a rotating roller pulls the fibers past a stationary knife, separating the seeds without damaging those longer fibers. After ginning, the separated lint goes through additional cleaning stages, such as back cleaners and saw-type lint cleaners, to remove smaller trash particles and neps. Finally, the cleaned lint is compressed into dense bales, which typically weigh around 227 kilograms, making them easier to store and transport to the spinning mill. For example, a 100-acre cotton farm harvested by a spindle picker might yield 500 bales of seed cotton. After ginning, this could result in about 150 to 200 bales of ginned lint, with the difference being the removed seeds and trash. The gin ensures that the cotton fiber is ready for the spinning process, maximizing usable fiber and minimizing waste. The main objective here is to open those highly compressed cotton bales clean. The cotton even further blend different cotton types and deliver a uniform flow of opened fibers to the next stage, which is carding. In the factory, this is actually the initial section of the spinning mill, and it's often a large, noisy area. So let's talk about the process details here. Bale opening starts with either automated bale pluckers or sometimes manual methods. These machines are designed to pluck small tufts of cotton from the bales. After that, the tufts are transported pneumatically, which just means they're moved by air currents, through a series of machines that have beaters and grids. The beaters, basically rotating cylinders with teeth or blades, strike the cotton tufts, knocking loose any dirt or dust. Then, grids or perforated screens come into play, allowing those impurities to fall through, while the lighter cotton fibers keep moving forward. Finally, dust filters collect all the removed dust and those fine particles. Next up is opening and blending. The cotton passes through different openers that gradually reduce the tuft size, going from large lumps down to individual fibers. If the factory wants to blend different cotton grades or types, for example, to achieve specific yarn properties like strength or softness, they feed them in together and mix them thoroughly at this stage. And in modern blow rooms, a chute feed system is used. Instead of making a lap, which is like a rolled sheet of cotton, the opened and cleaned fibers are blown directly into a chute. This chute then feeds the carding machines, ensuring there's always a continuous and consistent supply. For example, let's say a factory is aiming to produce a medium-quality denim yarn. They might blend 70% US upland cotton with 30% recycled cotton fibers right here in the blow room. The advanced sequence of beaters and air currents makes sure the blended cotton is clean and evenly mixed before it moves on to carding, which really helps prevent inconsistencies in the final yarn. And, if a lap former is used, you might see a 150-kilogram lap of uniform thickness, all set and ready for the next step. Alright, so the main objective here is to further open the cotton tufts into individual fibers, clean out any remaining impurities, and those tiny neps, which are just small knots of tangled fibers, and most importantly, to align the fibers into a continuous, untwisted rope called a sliver. This all takes place right after the blowroom, in a dedicated section of the factory that has rows of these large box-like machines. Now let's talk about the process details. The feed rollers take the opened cotton from the blowroom, whether it's in the form of a lap or coming directly from a chute feed, and feed it into the card. Then, there's the liquor in, which is a rapidly rotating cylinder with saw-like teeth. It grabs the cotton from the feed rollers, opens up the tufts even more, and transfers them to the main cylinder. Plus, it helps remove the heavier impurities. The main cylinder itself is a large wire-covered cylinder that rotates really fast, and the cotton fibers are carried right on its surface. Moving on, we have the flats, which are basically a series of stationary or slowly moving bars covered with wire clothing, and they're positioned super close to the main cylinder. The opposing actions between the cylinder and the flats actually comb the fibers, separating them, removing neps, and aligning them. This is, the primary carding action. After that, the doffer, which is a smaller wire-covered cylinder, strips the web of individualized and aligned fibers from the main cylinder. Then, the web condenser or trumpet comes into play. The delicate fibrous web coming off the doffer is condensed into a continuous, round, untwisted strand called a sliver by passing it through this funnel-shaped trumpet. Finally, the coiler delivers the sliver into these tall cylindrical cans, laying the sliver down in a helical pattern. So, here's an example to help you picture this. Imagine pouring a handful of tangled hair onto a brush and slowly drawing it through. Carding does this on an industrial scale. A carding machine might process anywhere from 100 to 200 kilograms of cotton per hour, producing a sliver with a precise linear density, like say 5 grams per meter. The quality of carding directly impacts yarn evenness and appearance. Poor carding leads to excessive neps and uneven yarn. The main objective here is to remove short fibers, which are called knôle, as well as any remaining neps and impurities. The aim is to achieve a very high degree of fiber parallelism, leading to a much smoother, stronger, and more lustrous yarn. This step is typically done for high-quality fine-count yarns, such as those used in shirting fabrics, fine apparel, or sewing thread. Usually, this process takes place in a separate section after carding, and it comes right before drawing. Let me walk you through the process details. First, there's the sliver lap former or ribbon lap former, where multiple carded slivers, typically 16 to 32, are combined and drafted slightly to form a uniform lap, which is then fed into the comber. This step ensures a consistent feed. Next comes nipping, where a pair of nipper jaws holds the leading end of the fiber lap. Then, during the combing segment, a rapidly rotating cylinder with rows of fine needles or combs passes through the fibers extending from the nippers, combing out short fibers or knôle and impurities. Finally, after the initial combing, a second set of rollers, known as detaching rollers, moves forward, grasps the combed fibers, and pulls them away. So the top comb, whether it's stationary or oscillating, further cleans and straightens the fibers as they're being detached. As each tuft of fibers is separated, it's overlapped and pieced with the previously combed tuft, which forms a continuous combed sliver, and then this combed sliver is delivered into cans. For example, if you're making a luxurious 100% cotton bed sheet, the yarn would most likely be combed. Combing might remove about 10 to 20% of the initial fiber weight as knôle or short fibers, but the remaining fibers are significantly longer, more uniform, and aligned. This allows for spinning exceptionally smooth and strong yarn that resists pilling and breakage. The objective here is to improve the uniformity, or evenness, of the sliver, to straighten and parallelize the fibers even further, and to blend multiple slivers for better consistency. In the factory, this happens in a section of machines placed after carding or combing, with multiple sliver cans feeding into each machine. So let's talk about the process details. Creeling involves placing multiple slivers, usually 6 to 8, sometimes even more, from either the carding or combing machines into cans at the creel. which is the input end of the drawing frame. Then, in the drafting zone, these combined slivers move through a series of drafting rollers. These rollers are arranged in pairs, and each pair rotates at a higher surface speed than the one before it. The front rollers rotate the fastest, while the back rollers are the slowest. Because of this difference in speeds, the slivers are stretched or drafted, which thins them out, and at the same time straightens and parallelizes the fibers. Now, let's look at doubling. Since multiple slivers are fed into the machine and then drafted back to the original single sliver thickness, any imperfections and variations in the individual slivers get averaged out. This doubling effect, honestly, makes a big difference in improving sliver evenness. After that, in the sliver coiler, the newly drawn sliver, which is now much more uniform and has highly parallel fibers, is collected in cans. Here's an example to make it clearer. If you feed 8 slivers, each weighing 5 grams per meter, into a drawing frame with a draft ratio of 8:1, you'll end up producing a single sliver that also weighs about 5 grams per meter. But this single sliver will be way more uniform and have more parallel fibers than any of the individual input slivers, thanks to the blending and drafting action. And really, this level of uniformity is crucial for smooth running in the next processes and for producing even yarn. So, the main objective here is to reduce the weight per unit length of the sliver through drafting, and to impart just a small amount of twist. This gives the sliver enough strength so it can be wound onto a bobbin and handled without breaking, basically getting it ready for the final spinning stage. The location for this process in the factory is a dedicated area, usually filled with large, tall machines that have many spindles. Here's how the process goes. First, cans of drawn sliver are placed at the input, which is called the sliver creel. Then, a roller drafting system, kind of like what you see in the drawing frame, attenuates or thins out the sliver to reach the required roving count. This draft ratio is actually much higher than what's used in drawing, so the sliver's thickness is reduced quite a lot. After drafting, the thin strand passes through something called a flyer mechanism. The flyer spins rapidly around the bobbin, inserting just a small amount of twist into the roving. And honestly, this twist is just enough to hold those attenuated fibers together. Winding onto bobbin. So the twisted roving is then wound onto bobbins, which are placed on spindles that rise and fall to build a well-formed package. For example, a drawn sliver of 5 grams per meter might be drafted down to a roving of 0.5 grams per meter, which is basically a draft of 10 times. This delicate roving is then given a low twist, say, around 20 to 50 twists per meter, just enough to provide the integrity needed so it can be unwound easily in the spinning stage. The roving bobbins are actually the direct input for the spinning machines. The objective here is to draft the roving to its final yarn count and insert the necessary twist to create a strong, stable yarn. This is really the crucial stage where fiber becomes yarn. And, in terms of location, this happens in the largest section of the spinning mill, which is often filled with rows of long, noisy machines. Let's talk about process details and examples of different methods. First, ring spinning. The mechanism here is actually the most versatile and widely used, especially for fine and medium counts, and for yarns that need high strength and good aesthetics. The process starts with placing the roving bobbins on the creel. The roving is first passed through a drafting system, typically 3 or 4 pairs of rollers, that further attenuates it to the final desired yarn count. For example, you might go from 0.5 grams per meter roving to 0.05 grams per meter yarn, which is a draft of 10 times. The drafted fibers then pass through a traveler, which moves rapidly around a ring. The rotation of the spindle, combined with the drag of the traveler, inserts twist into the yarn. The yarn is then wound onto a cop or small bobbin on the spindle. The advantages? Well, this method produces strong, smooth, and compact yarns with excellent hand feel.